An honor to have Dr. Gordon here to give us a talk on design or build your own game engine. Okay. Dr. Gordon works at California State University Sacramento. Okay. His area includes graphics and AI. Okay. His book on computer graphics, very good book. We use this as a very important reference for our CS 535 class here. Okay. And we are very glad that finally we have a chance to get him here to give us a talk on a very important subject, very important and recent subject, build your own game. So I'm sure we can learn a lot of things from Dr. Gordon's talk today. Okay. So let's give him a warm welcome.
Well, thanks for having me. It's an honor to be here. Let's see. Some of what I'm going to talk about actually does revolve around my textbook on computer graphics. There's a C++ and a Java edition. It's not meant to be a plug, but I may make references to it periodically. How many of you are taking or have taken a 3D graphics programming class from Dr. Chang? Or have knowledge in that area of rendering? Anybody with some OpenGL experience? Okay, so a few, that's about what I was expecting. Because of that, since many of you don't have OpenGL experience, that means that some of the slides you may not know what I'm talking about. But hang in there anyway, because the slides don't build on themselves. So if you don't understand one topic, you may understand the next topic. And if it inspires you to take the class, which I encourage you to do so, then you can come back and watch the video, and those parts that you didn't understand before, you would understand in the future. All right, so this talk is about building your own game engine. Not about building your own game, but your own game engine. So, how many of you have played with a game engine before? More people, right? Yeah, I knew that would be the case. So, a lot of you have some experience with game engines, but maybe you've never thought about making your own game engine. And then you might also be thinking, why might I want to do that? So we'll talk about that as we go along. For now, you can just say, well, because it's interesting. But there are practical reasons to do that as well. All right, so, first of all, the picture. So here, I mustn't stand there. I must remember. Sorry about that. Right, so the picture is supposed to designate here that there's an engine from which a lot of different games can be built. If you came in late, make sure to put your name in the box so you have a shot at getting a copy of the book. All right, so let's get started. So first of all, some terminology. Game design versus game architecture. So you all have experience with software design, and when you hear the word software design, what should come to your mind is how the lines of code are organized. But that's not what game design means. The word design in the game field refers to the design of the game, not of the code that implements the game. The code that implements the game, we refer to that as game architecture. So those are important terms to not be confused when you're talking about building games. These days, very, very rarely is a game built from scratch. They're all built on top of an engine. So what is the purpose of the engine? Well, it's to provide all of the things common to all games and to make it as easy for the game designer and game programmer to implement the game that they have in mind. So things like 3D rendering, managing the objects and models that make up the game, logic activities, game devices. There's a lot of math in graphics that even the game programmer may have to do, so making that as easy as possible. Physics, games always have physics because the world has physics, sound, AI for non-player characters, networking. Okay, of course, you don't want the game programmer, the game designer to have to reinvent all these things from scratch. Now, there are lots of game engines out there. This is just a partial list of a few of them. There's many, many more than this. If you look at Wikipedia, you can see that there are hundreds of game engines out there. Some of these you may have been played with. Unity and Unreal are very, of course, very popular now. But there are others too. Some of them are free. What about some popular games and what engines they are built off of? So I listed some of the major games and the engines that they're built off of. And you can see that all these games on the left are built on all different engines, some of which are commercially available or free, but some of which are proprietary, meaning that the company that made that game has their own game engine that they have not released to the public. That means that they're not only supporting their game, they're supporting their own game engine. That means they have employees that are working on the game and employees that are working on the engine. So if you know how to build your own game engine, then you can become a valuable employee of a game design company working on their engine. All right, so if you make a game, what's actually going on? How is it generally constructed? Here's the very high level overview of typical game structure. Since there's since there's always an engine involved, that usually has to be initialized when the game runs. Then the specific game that is being run within that engine has to be initialized. Then the game begins, and this is the part that the person playing the game actually experiences, is the game loop. Now there's many, many different designs for a game loop. If you're coming in late, put your name in the box so you have a shot at winning the book. So there's many, like I said, there's many different designs for game loops, some more efficient than others. But this is build your own game engine, so I want the very simplest possible game loop. So this is probably the simplest possible game loop. It's called a tightly coupled game loop. And that means that every frame, all three of these fundamental steps that have to happen in the loop are all done. Processing the player's input, processing any updates to the state of the game, and rendering the scene. Okay, now in a commercial game, this would probably not be the best design because it's inefficient. In some games, the rendering is the bottleneck. In some games, the logic update is the bottleneck. So the loop typically has to be tailored for performance for the game. But this is build your own game engine. We want to manage to get a game engine actually built that we can use to make games, and we're going to keep it as simple as possible. So we're going to use a tightly coupled game. Okay, so in the game engine that we're going to build here, that I built for my class, it's based on OpenGL. So OpenGL already has an animator loop built into it. It's actually called Animator in OpenGL, and it will render each frame as fast as it can. And in that animator loop in OpenGL, you're allowed to do whatever you want, write whatever code you want. And so, in our simple game engine, we're going to take that display function that OpenGL wants you to write, and we're going to call functions to do the logic update and grab the inputs and process those. Still a tightly coupled game. Okay, so you've probably heard this term before, one frame. That is, in the graphics world, that refers to each time we redraw the screen. In games, we're going to refer to it as, in a tightly coupled game loop, it's not only each time we draw the screen, but also, along with that, process the user's inputs and update the logic of the game. Okay, so the game engine that I built for my class and that this is all based on is called TAGE. And the reason it's called TAGE is it's historical. We had similar in-house game engines that we used for the class. The first one was called SAGE, but it used all deprecated OpenGL. So then when we re-engineered it to be compliant and shader-based, that became one called RAGE. And so then when it came time to re-engineer it again, basically started from scratch and wanted it to still have age at the end. So I chose T for TAGE, which works out nice for tiny game engine, but I didn't know what to do with the A. So I figured by the end of the semester, my students would have an appropriate word for that. It starts with A, so it's the tiny game engine. Students seem to like working with that engine actually better than they liked working with SAGE and RAGE. So they didn't fill in the A with what I was expecting them to fill in. Anyway, okay, it's written in Java, but this talk is sort of language agnostic, so could easily have just been written in C++. And so when we do see some code, I'm trying to write it in a Java/C++ type of a style, so not too married to Java. It uses OpenGL, and if you're going to use Java with OpenGL, you need to use a binding, so that would be like lightweight Java gaming library or Joggle. Well, my textbook uses Joggle, so this uses Java. Another thing that I wanted this game engine to match the code style of the textbook, because a lot of the students taking the game architecture class are also taking the graphics class. And so I wanted the code to be very, very similar. All right, so the code style for this really follows textbook. If you have played some with OpenGL, it's entirely shader-based, nothing deprecated in it. And it makes heavy use of, there's a great library called JOML for doing math and matrix operations. It stands for Java OpenGL Math Library. C++ there's a great library called GLM that you could use instead. Okay, primary goal, as simple as possible, because I wanted my students going in and modifying the game engine, not just building games off of it, but there's parts of the game engines that I didn't provide for them that I wanted them to write. So I wanted it as simple as possible so they could confidently go in and change the game engine. And they, pretty much all of them, made a lot of changes to the game engine. So I'm confident that the students, especially from a strong university as the University of Kentucky, could build your own game engine as well. Here are some of the games that students in the class made using TAGE. You can see a huge variety of types of games. A little bit later in the talk, I'll play a little video so you can see what something looked like while they're being played. Students are so creative to come up with games I never would have thought. All right, so now let's dive into organization of this tiny game engine. And again, the purpose of me showing you this is not for you to be impressed with my little game engine, but to show you how you could make your own game engine. You don't have to design your game engine exactly the same as mine. And along the way, I'll show you little places where I made a choice, and you could make a different choice. All right, so there's a lot of things that a game engine should provide to make it as easy as possible, as flexible as possible for the game programmer. I've put the ones here with this red box surrounding it as sort of the core. If you're going to make a game engine, you really need at least these things. This is sort of the core of the game engine. And then, of course, these other things, well, they're important too. Input manager, handling sound, physics, these are all really important too. But you can save those for later. These are really the core that you've got to solve first, after which the rest should fall out more clearly. All right, so here is a UML diagram of those same components. I don't intend to go through all of this, but go through a little bit of it. So for instance, the game engine, if you're writing a game, you instantiate the engine. The engine has a HUD manager, a light manager, a scene graph, a render system. The render system has potentially multiple viewports, a bunch of object shapes, a render queue. There's the scene graph has a bunch of game objects, node controllers, there's textures, render stations, a whole bunch of different types of shapes that this little engine will support. So let's start by looking at, I guess you could say, what I found to be a good starting point was the objects and their shapes. All right, so if you know anything about 3D graphics, you know that usually the way that it works is you have models that comprise objects. And when you're rendering a scene, what you're essentially doing is rendering these objects. So that's the way the game, since it's using OpenGL, is necessarily has to be organized. We have game objects that are being rendered, and I've separated the object from the shape. So why? Well, imagine you have a game where you're being attacked by zombies. Well, zombies usually come in big groups, right? So you've got, say, 50 zombies. They all are probably using the same model, but there's 50 objects in one model. So the model for the zombie, you would want to just read in once. It's probably stored on a disk somewhere. Maybe you made it in Blender or something, and it's stored. So you load that in once. You don't want to load that in for every zombie. That would be really slow. So by separating these, you can have multiple objects, so all sharing the same model. And so that's captured here. All right. So here's an overview of how the object and the object shape are related. So each object has a shape, but the reverse is not true. Shape may be for multiple objects. I decided to include several predefined shapes, spheres and planes. You might want to stick a planet out there by making a sphere or something. Bouncing ball. Figure really simple shapes. Why make the programmer have to make an OBJ file for that loaded in? So, okay, but of course they're going to want to put their own models in there. So the simplest way to do that is to support OBJ file format. So in my textbook, there is a simple OBJ loader. It's definitely one of the worst OBJ loaders in the world. It's really stripped down because the goal of the book was to explain how it works. And so it's a very simple, limited OBJ loader, and that's the one I used in the engine. So so I have a question for you guys, for one of you. Who am I going to ask? Evan Jones. So my question for you is, do you want a copy of the book in C++ or Java?
I'll take Java.
Java. Both the other books I have are C++, so the next person's stuck with C++. Okay, so it just uses the OBJ importer that's in the book. So if you've got a really fancy OBJ model that has a bunch of stuff that doesn't support, you may have to adjust your model. So this is a tiny game engine. All right, Oops. All right, so manually defined models, if somebody actually wants to put all the vertices and texture coordinates in by hand, right in their code, you can do that. Skybox, that's another shape. Simple terrain. Those of you taking the graphics class, have you got to terrain yet? Have you done height mapping? Not yet. Okay, you'll get to height mapping, and so that's in here too. It just matches the code in the book. Each object also has an instance of a class called render states, which enables you to set if you want it to be rendered solid or wireframe, enable it or disable it, whether it's textured or just has a solid color, whether it's transparent. Actually, truth be told, I haven't implemented transparency yet. It's trickier than trying to figure out a way to do it really simple. I haven't figured it out yet. So each object also has matrix transforms. In game engines, every game object, every object in your game comes with, standard way to do it is 3 transforms. One for moving, one for turning, and one for resizing the object. So the matrix transforms associated with moving objects around during gameplay are held in the game object, not in the shape. Okay, design decisions. Should the lights and the cameras, should those be game objects? In many game engines they are, in TAGE they are not. Pros and cons to both. Sometimes I'm in there and I say, I wish the light was a game object. But in Sage, the lights were game objects, and there were times that I was saying, I wish the light wasn't a game object. Here's a little drill down into the classes. So the game object class has a shape, texture image, and one of these render states classes, you can see the matrix transforms are in the object class. Okay, what makes up a shape? So those of you who've done a little bit know that these actual rendered shapes are built out of vertices. Each vertex has a location in 3D space, X, Y, Z. Probably also has a texture coordinate and a normal vector associated with it. All those things are part of the shape, and they would be loaded in, for instance, in an OBJ file, or would be loaded in automatically from one of those predefined shapes. So that information is not in the game object, but in the game object's shape. Of course, the renderer OpenGL is going to need all this data to render the object. And so there are many types of game objects. Hopefully you remember your UML. This means has a. This means is a. Your software engineering class. Okay. The shape also stores lighting information. We'll talk about that. Let's talk about the camera. So again, if you've taken the graphics class, you've had to control a camera, define and control a camera. That's sort of the viewpoint of your world. So the game takes place in a 3D world that you've made. How does that world look? It has to be projected on a 2D screen. So that's done in the camera. Let's talk about the camera. So this is a review if you've had the graphics class. This picture's out of the book. You guys in the graphics class seen this picture before? So cameras are defined as having a location and an orientation. You can think of the orientation as the direction that they're looking, but there's a little more to it than that. So when you see your scene rendered on the screen, you're seeing it from the camera's vantage point. Cameras are defined by having an orientation, which is a set of 3 orthogonal vectors, usually left-handed coordinate u, v, and n, and a location, x, y, z. And in the TAGE's camera class, there is an important function that computes what's called a view matrix. So those of you in the graphics class probably know what a view matrix is. By now, I'm sure that was back in chapter 3. And so that is, the view matrix gets multiplied in with all the other 3 matrices, the rotation, scale, and transform, when it's time to render the object so that it's rendered from the right vantage point. All right, so there's a class called render system. It has some number of viewports. We'll see the render system in a minute. Viewports would be like if you had a game that had multiple panels or windows. So like you could view the racetrack from the race car or from above. Commonly for games that have multiple viewports. And in TAGE, each viewport has one camera. And you can see here are the items, the orientation of the camera, the UV vectors, the location, and the view matrix, which can be imputed on demand. These classes over here, vector 3F, matrix 4F, those are JOML classes. Remember that math library that I told you about that this uses? All of those structures that we need for matrix, algebra, and other math are handled in JOML classes. Again, if you did this in C++, you would use GLM classes, and I think in GLM, these are called vec3s, and that's called mat4. That's probably what you're using in your graphics class. Another couple pictures from the textbook here is how the view matrix is computed. You don't want the game programmer to have to compute all this stuff. So the engine will compute that will do this computation. If you ask the camera, give me your view matrix, it will do that. Actually, you don't even want the game programmer to have to say, give me the view matrix. The render system should ask the camera for its view matrix. All right, we're going through all the core elements. In fact, in this talk, we're only going to really be able to dive into these core elements. We'll talk about these briefly at the end, but we've only got an hour, so. Let's talk about lights. This picture is also from the book, maybe you've seen this one. How is lighting done in graphics? So in 3D graphics, lighting is not done by actually shining a light. That is extraordinarily computationally expensive. Imagine having to model quadrillions of photons and how they bounce around and which ones reach your eye. I mean, that would not be computationally feasible. So instead, the way graphics handles lighting is you define what lights you want in your scene. And when you render the object looks at the lights and say, how should I be rendered? There's a light over there, okay, I'll render these pixels a little brighter, and these ones a little darker. So the most common lighting model used in graphics, not the only one, but the most common one is the ADS lighting model, where reflection is modeled by three components. Ambient lighting, which is lighting that sneaks around everywhere, even if there isn't a light hitting it. Diffuse lighting, which is based on the angle of incidence of the light. And specular lighting, which is based on whether or not the light will reflect directly into the camera. So ADS lighting is what's done in TAGE, and all the code for the ADS lighting is the same as covered in the textbook. All right. So with that, let's see who gets another textbook. You're stuck with C++ this time. Zane McCoy. We're just sitting next to each other. This is a conspiracy. Remember, don't stand there. So lighting, ADS lighting is commonly modeled in different ways depending on the type of light source. Besides just sort of the global ambient light, it's common to design positional lights, directional lights, and spotlights that all have slightly different characteristics, and there's good uses for all of them. All three of them are described in the book. probably, Dr. Cheng's class have already gotten into the lighting chapter, so you're probably familiar with that. TAGE supports, besides ambient lighting, it supports positional light and spotlights, but not directional lights. Not that directional lights aren't useful, they're just not as useful as positional and spotlights in games. So that might be counterintuitive, but true. All right, so I decided in my simple game engine to make a class called Light Manager, because we not only have lights as objects, but there might be a lot of lights in the game, and we might want the programmer to be able to generate lights on the fly. Imagine a type of game where maybe you're building cities or something. So you build a building and now turn on its lights. We'd like to have that flexibility, and unlike models, we don't have to read in from the disk light information. So why not make lighting dynamic, that the programmer can write a game that makes and destroys lights at runtime. All right, so we need a light manager for that, so that the programmer can have multiple lights in their game. Here's all the sorts of information that a light should have. Its ambient, diffuse, and specular characteristics, like you saw in the previous picture. By the way, ambient, diffuse, and specular information is stored as RGB values. So you probably know what RGB is. And so there are little float arrays that have the RGB values. I also went ahead and included other factors that are useful. Cutoff angle and off-axis input. Those are for spotlights. The location of the light. That's another thing. Now, it's probably not immediately obvious even to, yes?
Just a quick question. So earlier on you were saying that lights are not game objects.
Not in my game,
Okay.
not in my engine, but in some engines they are.
Okay, but what you're describing is still in yours, right? So what's the difference between a game object and not a game object? In this case, it still has attributes.
Right, so that'll be more clear when we look at the scene graph. Scene graph contains game objects, and game objects are things that are actually rendered. We actually don't render lights. Lights are not a theme in the ADS model. We're never rendering a light. Now you might think, well, wait a minute, if I have a headlight on, well, that's not an example. If I have a desk lamp, that is a thing, right? And I want to show the desk lamp. Well, what you do is you make a desk lamp game object, render it there, and then also have a light at that same position. Actually, the ADS lighting model is more accurately not a lighting model. It is a reflection model. So I probably should have put that on the slide. But great question. Okay, now, those of you taking the, oh yes.
So you say that lighting information is not loaded from the disk?
Right. Oh, with one exception.
Normal vectors, right?
Okay, so normal vectors are usually part of a model.
Which is
So-
loaded from the disk.
That's true. But that's not going to change if we add a light. That's part of the model. And the model interacts with the light according to its normal vectors and actually according to its material definitions. That's another thing that may be something that's loaded in from the disk for a particular object model, object shape, is its material ADS characteristics, because that's part of the model. But that's not actually part of the light object, nor is the normal vectors. That's not part of the light object, because there may only be one light. There may be all these different models. Each have their own normal vectors, and each have their own ADS material characteristics, and they're all going to interact with this one light. And the only thing we need to store about that light is those characteristics that we saw before. and they're not generally read in from disks. But you could, in your game engine, if you wanted to have a way of storing light information in files and reading those in, you could do that. Okay, so those of you who have implemented some of your graphics stuff, your graphics class, know that to complete the lighting, we need material ADS characteristics, but those are not coming from the light object, but from the object shape. Now, right now they're just stored in the object shape. Arguably a better design would be to have a separate class called material and attach a material object to a shape object. That would be more flexible, but I didn't do that. We're doing fine. But if you do your own, you should consider having a materials class. Sometimes I wish I had done that. Okay, now everything we've done so far actually has very little to do with games and has everything to do with just rendering in OpenGL. We're now going to see the first thing that is specific to games, and that's the scene graph. Pretty much every game engine, almost every game engine, there may be strange stragglers somewhere, but virtually every game engine provides what's called scene graph. And that is a structure in which your game objects are stored. And it's usually a tree, a simple tree. And it turns out that is enormously useful to a game designer. Why? Because it enables the game designer to build hierarchical objects and systems. So for instance, if you want to build a house and put some things in the house, and then it turns out it's a Wizard of Oz game, and a big hurricane twister comes along and moves the house, all the objects that are in the house will stay with the house. You won't have to move all the objects individually. That's one example. Another example, say you want to have a solar system. That's a hierarchical system. It's a little different than a hierarchical object, but as the Earth goes around the sun, the moon goes around the Earth, it goes right along with the Earth. You don't have to compute that strange trajectory of the moon. You simply give the relative position of the moon relative to the Earth, and then as the Earth moves, the moon will move too. So that's super useful for games. And so pretty much every game engine has that. So your tiny game engine that you're building will have to have that too. Turns out it's not very hard to design a scene graph support. Actually, here's a picture of Unity, and where you'll find Unity's scene graph is up in the upper left. Hence, you may not have known that was a scene graph, depends on how much use you made of it. You just hang all the game objects off the root. It's still a tree, it's just a very flat tree. But anyway. Okay, so in TAGE, I did not put the lights and camera in the scene graph, but many game engines do, in fact. In Unity, there's the camera and the light in the scene graph. Advantages and disadvantages. Yeah, so here's another example of objects in the scene graph. Sometimes people organize the objects using hierarchy in the scene graph for organizational purposes. Others do it so that because it's an integral part of the game and how the objects interact with each other. Okay, there are off-the-shelf scene graph APIs. You don't have to build the scene graph yourself from scratch. Here are a few. Oops, I pushed the wrong button. Here are a few of several off-the-shelf scene graphs that you could use in your tiny game engine. I chose to write mine from scratch. I mean, it's only a tree. You guys know how to implement a tree. I felt more comfortable implementing it myself. So the key feature of the scene graph is that here's an actual game object, wall, that's in the game. It has to be rendered. So there's a bunch of matrices involved. There's of course the vertices and their locations. But then there's that translate, rotate, and scale matrices that we use to move the wall around. Right? And then there's the view matrix that has to be multiplied in as well. What the scene graph does is it says, okay, what is the actual position of the wall? It is whatever its matrices are concatenated with its parents' matrices. So what the renderer has to do, or somebody somewhere in your engine has to do at every frame, is to correctly compute every game object's matrices. And that's generally done by propagating the matrix multiplications down the tree. Here's the class organization for the scene graph. It's related to scene graph. So the scene graph class, it has a bunch of game objects that I have stored in a Java array list, basically an array. And one of them is the root. Every game object has one parent and multiple children. So basic tree. I used a Java hash set so I could grab the children more quickly. Other than that, these are the other things we already saw. But then we have to give the game programmer the ability to set an object's parent, place it somewhere in the scene graph. Maybe add a child, get an iterator for the children. That's all done in the game object class. And then there's this one important function called update that basically says start at the top of the tree and figure out everybody's matrices. Now there's actually optimizations to that I did in TAGE, but I won't describe them here. You don't actually have to compute everybody's matrices every single frame. All right, so here's an example of updating every game object's position. All right, so the way it's done is that previously I told you, let's go back a slide. Previously I told you that every object has three matrices, one for translate, one for scale, one for rotate. Actually, there's 6 matrices. There's translate, scale, and rotate local. Translate, scale, and rotate world. And world means where they are in the whole world. Local means where they are relative to their parent. And so the worlds are computed from the locals. So at any given time, the world translation matrix is the parent's world translation matrix concatenated to your local translation matrix. Okay, whoops. So this just summarizes that. In order to update everybody, anytime a node changes, moves or changes in any way, you have to update all its children. So what does update do? You get the parent's world concatenated to your world, do the same for the rotation, the same for the scale, and then iterate through your children and telling them to update. So it's kind of recursive. This is sort of a pseudo recursion, right? You're not actually calling it on yourself, you're calling it on your child's object. You didn't get all that right away? Don't feel too bad. Yes?
So you don't actually just update your children. You update the entire subtree that has that node as a root, right?
Yes. Correct. Because when you do this for a child, it's going to call this function, which is going to call. It's going to do all those lines at the bottom one. It's going to do it for its children too. Yep. Okay. Now we're to the core. We've got enough of our components that we can actually look at the real core of the game engine, which is the render system. Okay, so this is a picture from the book. Hopefully you've seen that. If you haven't, don't worry about it. Just know that rendering in OpenGL is done in hardware on the what's called the graphics pipeline. Information such as vertices go in these buffers called BBOs, and other things that are the same for every object, like lights, go into things called uniforms. The render system has things that anything related to rendering shapes in OpenGL. So it's going to be the vertices, textures. It's going to be an OpenGL canvas, and some of these are functions that you would that the end programmer would actually call directly, and some of them would be things called within the engine. So I tried to separate those things that are time intensive, that require reading in from the disk, and do those once before the game starts, versus things that are done at every frame. So for instance, loading shapes, compiling the shaders that make up the actual rendering code, loading textures and skyboxes, those are just done once. So in my tiny game engine, I said, you can't load another object from the disk once the game starts. Any sort of a shape, not objects, you can make new objects, but shapes that are actually read in from the disk, you have to read in every shape you could possibly need in that game before the game starts, even if they end up not being used. And then at every frame, the engine is going to call a function that the user, the programmer, is expected to write called update. And the programmer who's designing the game can put anything in there he wants. And that's where the actual gameplay would be programmed by the programmer. Now, loading lights, the lights could change, we said that. The view matrix has to be computed. All this stuff has to be done every single frame. I actually have the basic code for the renderer here, and I'm only just going to flash them up on the screen because if I went through all the code in detail, it would take another half an hour. But I'll put it up there for the benefit of those of you taking the graphics class to see that it's things that you should recognize. For each object in the game engine calls render. So that means it loops through. Actually, what it does is it asks the scene graph to take all the objects that need to be rendered and put them in a render queue, and then it loops through the render queue called render. All right, so for each object, it has to accumulate all the relevant data that it needs to render it. So some of those are in uniforms, and some of them are in VBOs. It has to build the model matrix, and let's see. And you probably remember that if you are dealing with the lighting and the normal vectors, that you have to, those of you in the graphics class may remember, that you have to do the inverse transpose of the model matrix for the lighting. Here are all of the, this actually sends all the data to the uniforms. By the way, the lighting has something that you probably haven't seen in the textbook yet and may not get to. And that is, since it's a variable number of lights, we don't know ahead of time how many lights are going to be created during the game. The only structure that you can use in OpenGL for that is called an SSBO, Shader Storage Buffer Object. So if you get to the point where you're designing yours and say, wait a minute, how am I going to handle an arbitrary number of lights? Look up shader storage buffer object. And that's how you can do that in OpenGL. Okay, let's see here. There's some if statements in the shaders, which are inefficient in shaders, but they're simple. So if the render state is wireframe, you're going to render it differently than if it's solid. This sends all of the buffer information, so that would be vertices, texture coordinates, normal vectors down the shader pipeline, and ultimately, say, draw arrays, which I'm sure you've all included in the graphics class. I've written that line of code probably many times. And that's going to happen for every object in the scene graph. If you're curious what the shaders look like, it should look very much like code that you've seen in the book. Speaking of which, I have one more book that I haven't given away yet. Saltman Alsaman. Remember the vertex shader, those of you in the graphics class have probably done this, where to figure out the position of your object. You can take your object, multiply it by its model matrix, then the view matrix, then the perspective matrix. And fragment shader, where the color is determined, that's where all the lighting computations happen. So this is a little longer than any of the lighting computations in the textbook, but that's because every light, you can't really hard code the lighting information because we don't know what lights the user is going to ask for. And so the last component I'm going to mention is the actual driver for the game loop. Variable frame rate game. That's a class that I put in there that the programmer is expected to extend. So the way that the end programmer writes a game is by extending variable frame rate game, implementing these functions, and calling these functions at the appropriate time. I decided to require all the assets, like OBJ files, texture, images, to be placed into these folders with these names. So I had a set map asset structure. So now, suppose you finished making TAGE, made the game engine, how would the end programmer actually use it to make a game? Well, here's a hello world in TAGE. So hello world in TAGE is you make a game that extends variable frame rate game. You make game objects, shapes, lights, and textures for whatever you want to put in your game. This main has to be there. That'll initialize the system and start the game loop. You have to write load shapes in which you instantiate any of the shapes. You can use the imported model from the book that I told you about, because that's in TAGE. Or you can use TAGE's calls to instantiate spheres and things like that. Same with loading the textures. Same with building the objects, which is just associating shapes with textures. Associating objects with shapes and textures. Setting up whatever lights you want using the calls to TAGE. Setting up anything else you want. In this case, all I did was set up the main viewport. And then you have to write a function called update, in which you put anything you want to have happen in real time in your game. And you can either use an input manager, or you could use Java Compressed and override that to run your game. Actually, let's do that. Let's run this hello world game, that code I have here. It's very exciting. It just has a dolphin. That spins around in a circle. press the 1 key, you have to click in the window. Press the 1 key and it stops spinning. Press the 1 key and again, it resumes spinning. And that's the entire game. But, I'll show you a quick video of some of the games my students made using TAGE. A 1-minute video. So here's a first-person shooter, the robots attacking. The robots are actually animated models. I haven't talked about the animation subsystem that I put in there. That was written actually by a student. This is called Horrific Maze. And you're the little mouse trying to avoid all these horrible hazards. That mouse is so cute. So what's the name of this television show where you, Wipeout? So my students made a Wipeout type game. You can tell one of the main deficiencies of the tiny game engine is it doesn't have shadows. However, a few of my students added shadows to TAGE. And one of them was this student who made a car racing game. You can see they added shadows. They didn't fully get the collisions working right, as you can see. I thought this was clever how you can accumulate a banana and then drop the banana. This is a Rock'em Sock'em robots playing hockey. This was we ran this game at our yearly engineering expo, and it ran continuously for 4 hours with a bunch of middle school students playing off. So even with a tiny game engine, you can do a lot. We're almost done, just a couple more slides. Sorry, I went over a little bit. The little document that I gave them showed exactly the set of steps that happen. So here is the Hello World program that the game programmer has to write, and the functions they have to write, and the functions they have to call. And this is sort of the order of steps that things happen in when you set up a game and start it running. And so a lot about designing your own game engine is figuring out what has to be done before this, what has to be done before that, and coming up with a good order of things that's clean and stable. I won't talk through all that. So I didn't describe several things. I didn't describe that I actually have, other than those shaders that you saw, I've got other sets of shaders for particular things like lines and skyboxes. There's a whole set called node controllers that we didn't talk about. Full screen exclusive mode, maybe you know what that is. I didn't describe any of that. I didn't describe multiple viewports and how you can add borders to them. Height mapping for terrain is in there. It just follows what's in the textbook. So there's 3 of you that are armed with that. Let's see, camera controllers, like orbit controller, a chase controller. I didn't put how that's done in here because actually that's an assignment I give the students to do, is write a camera controller and add it to TAGE. HUDs. TAGE's HUD system is really terrible. That's heads-up display. That's for a little text at the bottom. You can see who's winning. Scores. Let's see. There's a bunch of options for how the matrices can be propagated through the tree. There's a whole bunch of render states. Maybe some of you in the book have gotten to environment mapping, and that's a render state option. Things like that. Then there's all these extension packages that are important too, like supporting game pads. Your game programmer might want the game to support a gamepad. Java doesn't come with support for a gamepad, but there are, C++, I don't think, but there are libraries then we'll do that. Physics, there's a JBullet library, which is a wrapper for Bullet, that one of my students made a simple wrapper. Audio, OpenGL is pretty easy to use, and I had a student that made a wrapper for it, make it even easier for the end programmer. NPC behavior, you can just program it, you can have the programmer program it ad hoc, or one of my students wrote a subsystem for what are called behavior trees. That's a data structure that is commonly used to control non-player characters in games, and it's kind of specialized for games. It's an AI technique that you generally don't learn in an AI class because it's really only useful in games. Animation, this is one of the most complex sections in there. You can do a whole talk just on animation. Now there, of course, is animation because of that game loop. It's an OpenGL animated loop, but there's a separate kind of animation which is having a model that is animated. And OBJ does not support animation. So if you want to have animated models, that means you have to have another format for storing animated models, and that has to be handled in the renderer also. That's pretty complex. If you manage to get everything working without the animated model thing, you still got a nice little game engine, and then you can tackle getting animated models to work, which is about as complex as the whole rest of the game engine. Here are things that TAGE does not have at this time. Yeah, like I said, it has terrible bullet support. It's just straight text, and that's it. It doesn't have shadows. It doesn't have transparency. It doesn't have generalized event handling, which would be nice. It has a terrible, very stripped down OBJ importer because it's the one in the textbook. Although it supports normal vectors, it doesn't have what's called normal mapping, which is a common way of adding surface detail to an object, or simulating surface detail to an object. That would actually be really easy to add. I'm thinking of adding that maybe before next semester. It has its own animated model file format that's a Blender plugin. It would be nice if it used more standard, industry standard animated model files. No procedurally generated terrain, only simple height mapping. No 3D textures, only 2D textures, and skyboxes, but not skyboxes. Although the programmer could do that themselves by just taking a sphere, texturing it, and having the game take place inside of it. That's my last slide. So, yeah, questions? Yeah, you've been asking great questions. I appreciate it.
So this question is about your OBJ loader.
Okay.
What features of OBJ files does it not support?
Okay, so it's probably easier for me to answer what it does support. So you know how an OBJ file is laid out? There's lines that start with V, lines that start with VT, lines that start with VN, and that's it. So there's a lot of useful things that OBJ does support, like having a model that's built up of several submodels. My old loader doesn't handle that. There's loading in materials. Mine just ignores those lines.
Also, what?
Oh, and I'm sorry, and it also handles the F, faces. You have to have the faces to build the actual triangles. Right. And it only supports triangles, it doesn't support quads. So basically I tell my students, they find a great model, they want to put it in their game, say load it into Blender, and then tell it to triangulate the faces and collapse it all into one model.
And my other question was, what data structure does it load the model into?
Okay, so when it loads an OBJ model, what it does is sort of the standard thing that you do in OpenGL is you take all of the vertices and you load them into a vertex buffer object. Then you load all the texture coordinates into a parallel vertex buffer object, load all the normals into a third vertex buffer object, so that they're ready to go for OpenGL, just to send down the pipeline. And then sort of the meta information about that object, like its initial position, its initial rotation. Well, no, I'm sorry, we're talking about shapes, so that wouldn't be done there. I'm trying to remember if there's anything else we need to store about the shape. Oh, well, let's see, because each shape has render states associated with it. So we would initialize a render state object and set default values for that. But the actual data, vertex data, goes straight into vertex buffer objects.
Okay, so shall we thank the speaker?
Excuse me?
I said, shall we thank the speaker?
If you still have questions, Dr. Gordon will be here, for another hour. So
I'm not going to miss out on that piece. So.
Yeah, so you can ask me any questions after the talk. We thank Dr. Gordon for giving us such an exciting talk. And I noticed that the system now is called the TAGE, Tiny Game Agent. I hope next time when you visit us, that thing will be called BAGE, Big A, Game Agent, or eventually huge A, Game Agent.
And MAGE, medium-sized.
Medium-sized. Oh, thank you very much.